Welcome to this hands-on project on FlashAttention. In this tutorial, we are going to explore what FlashAttention is, why it matters, and how it improves the performance of modern deep learning models, especially transformers. We will not treat FlashAttention as a black box. Instead, we will build intuition step by step and connect the theory to real code and real measurements. Throughout this project, we will cover several key topics. First, we will explain what FlashAttention actually does and why it is such an important optimization for attention mechanisms. Then, we will install the FlashAttention library and verify that it works correctly in our environment. After that, we will compare FlashAttention against a reference PyTorch implementation to ensure correctness. Finally, we will run speed and memory benchmarks to clearly see how FlashAttention compares to standard PyTorch attention in practice. Before we go further, it is important to understand the hardware requirements. FlashAttention is not a pure Python or CPU-based optimization. It relies on low-level CUDA kernels and therefore requires a Linux system with an NVIDIA GPU and a properly installed CUDA toolchain. If FlashAttention is not available on your machine, this notebook is still useful because it will automatically fall back to baseline PyTorch experiments so you can follow the logic and comparisons. There is also a very important GPU requirement to keep in mind. FlashAttention only works on Ampere or newer NVIDIA GPUs, which correspond to compute capability SM80 or higher. Examples include GPUs like the A100, A10, RTX 30 series, RTX 40 series, and H100. Older GPUs, such as the Tesla T4, which is based on the Turing architecture, are not supported, even if CUDA is installed correctly. If you are running this notebook on an unsupported GPU, do not worry. In that case, the code will automatically switch to PyTorch's scaled dot product attention, also known as SDPA. This allows us to still verify correctness and compare performance behavior, even though we cannot run the FlashAttention kernel itself. This way, everyone can learn the concepts regardless of hardware limitations. In the next section, we will start by building intuition about the attention mechanism itself and understand why memory usage and data movement are the main bottlenecks that FlashAttention is designed to solve. To understand what FlashAttention is, we first need to recall how attention works in transformer models. In simple terms, attention allows a model to decide which parts of the input are important when producing an output. This is done by comparing queries, keys, and values and computing attention scores that determine how information is combined. While this mechanism is extremely powerful, it is also very expensive in terms of memory and computation. In standard implementations of attention, the model explicitly constructs a large attention matrix. This matrix has a size proportional to the square of the sequence length. For long sequences, this quickly becomes a problem. Not only does it require a lot of memory, but it also forces the GPU to repeatedly read and write large tensors to and from memory. In practice, this memory traffic, not the math itself, becomes the main bottleneck. FlashAttention is an optimized way to compute attention without ever materializing the full attention matrix in memory. Instead of computing everything at once and storing intermediate results, FlashAttention fuses multiple steps of the attention computation into a single GPU kernel. It processes the data in small blocks, computes partial results, and immediately discards what is no longer needed. This drastically reduces memory usage and avoids unnecessary memory transfers. The key idea behind FlashAttention is that it is memory efficient rather than just compute efficient. Modern GPUs are extremely fast at performing mathematical operations, but they are relatively slow when moving data back and forth from memory. FlashAttention takes advantage of this by keeping data in fast on-chip memory such as GPU shared memory and registers as much as possible. This allows the GPU to spend more time doing useful computation instead of waiting on memory access. Why does this matter in practice? Because attention is at the core of large language models, vision transformers, and many other modern architectures. When attention becomes more memory efficient, we can train and run larger models, use longer sequences, or increase batch sizes without running out of GPU memory. In many cases, FlashAttention also leads to significant speedups, sometimes several times faster than standard implementations. To make FlashAttention easier to understand, let's walk through a simple example. Imagine you are reading a sentence and trying to understand the meaning of one word by looking at all the other words. For example, in the sentence, "The cat sat on the mat," the word "sat" needs to pay attention to "cat" and "mat" to fully capture the context. This is exactly what attention does in a transformer model. In a standard attention implementation, the model compares every word with every other word at the same time. If the sentence has 5 words, the model creates a 5x5 table of attention scores. Each cell in this table tells the model how much one word should pay attention to another word. For short sentences, this is fine. But if the sentence has thousands of tokens, this table becomes extremely large and consumes a lot of GPU memory. Now imagine a much larger example, like a long document with 10,000 tokens. A standard attention implementation would try to build a 10,000 by 10,000 attention matrix and store it in memory. Even though the model only needs the final output, it still has to create and store all intermediate results. This causes massive memory usage and slows everything down, because the GPU has to constantly move data in and out of memory. FlashAttention changes how this computation is performed. Instead of building the entire attention table at once, FlashAttention processes the input in small chunks. It takes a block of queries and keys, computes their attention scores, applies the softmax, multiplies by the values, and immediately accumulates the result. Once a block is done, the intermediate data is discarded instead of being stored in memory. You can think of this like reading a book page by page instead of printing the entire book on a huge table. With the standard approach, it is as if you print every possible word-to-word comparison and spread them all out at once. With FlashAttention, you read only what you need, process it immediately, and then move on. The final understanding is exactly the same, but you never waste space storing unnecessary information. The important thing to note is that FlashAttention does not change the output of attention. If you compare the results of standard attention and FlashAttention, they are mathematically identical, up to small numerical differences. The only difference is how efficiently the computation is performed. FlashAttention avoids large temporary tensors and keeps most of the work inside fast GPU memory. In this first code block, we are setting up the Python environment so that our project can find and import local source files correctly. This is a very common step in real-world research code and machine learning projects, especially when the code is organized as a repository rather than a single script. In this block, we are preparing a clean and compatible PyTorch installation. This step is optional, but it is highly recommended when working with low-level GPU libraries like FlashAttention, because version mismatches are one of the most common sources of errors. First, we uninstall any existing versions of PyTorch, Torch Vision, and Torch Audio. Even if PyTorch is already installed, different versions may have been built with different CUDA configurations. Removing them helps us start from a clean slate and avoids hidden conflicts later on. Next, we install a specific version of PyTorch and its related libraries directly from the official PyTorch CUDA wheel index. This is important because these wheels are precompiled to work with a specific CUDA version, in this case CUDA 12.8. Using the official index ensures that PyTorch is correctly linked against CUDA and can fully utilize the GPU. We explicitly pin the versions of Torch, Torch Vision, and Torch Audio. This guarantees compatibility between the core PyTorch library and its ecosystem packages. When working with performance-critical extensions like FlashAttention, even small version mismatches can cause runtime errors or silent performance issues. It is also worth noting that installing CUDA-enabled PyTorch this way does not require a separate system-wide CUDA installation. The necessary CUDA runtime components are bundled with the wheel, which makes the setup much easier and more reproducible across different machines. By the end of this step, we have a known stable PyTorch environment that is ready for FlashAttention. In the next section, we will verify that PyTorch can see the GPU correctly and that CUDA is available before moving on to FlashAttention itself. In this step, we install FlashAttention itself. Unlike regular Python libraries, FlashAttention is distributed as a precompiled binary wheel because it contains highly optimized CUDA and C++ kernels that run directly on the GPU. The installation command points to a specific release hosted on the official FlashAttention GitHub repository. This wheel is carefully built for a particular combination of software and hardware: CUDA 12, PyTorch 2.8, the C++11 ABI Python 3.12, and a Linux x86-64 system. All of these details matter because even a small mismatch can cause the installation to fail or the library to not load correctly. By installing FlashAttention this way, we avoid compiling the library from source. Compiling FlashAttention requires a full CUDA toolchain and can take a long time, so using a pre-built wheel is the fastest and most reliable approach when one is available. It is important to understand that this installation will only succeed if your system meets the requirements discussed earlier. You need a Linux machine, an NVIDIA GPU with Ampere or newer architecture, and a compatible CUDA-enabled PyTorch installation. If any of these requirements are not met, FlashAttention will either fail to install or will not run at execution time. Once this command completes successfully, FlashAttention is available as a Python module and can be imported just like any other library. In the next section, we will verify the installation and confirm that FlashAttention is correctly detected and usable before running any experiments. In this section, we're doing a quick environment check to make sure everything we installed is actually working. Before we run FlashAttention benchmarks, we need to confirm three things: what Python version we're using, what PyTorch version is installed, and whether CUDA and the GPU are correctly detected. This step saves a lot of time because many FlashAttention issues come from a mismatch in versions or a GPU that isn't supported. The code starts by importing platform, torch, and textwrap. The platform module tells us basic system information like the operating system and Python version. Torch is PyTorch itself, and it also gives us access to CUDA and GPU info. Textwrap is imported here for convenience in later printing or formatting, although in this exact snippet we're mainly using platform and torch. Next, we print out the Python version, the platform information, and the PyTorch version. This is important because the FlashAttention wheel we installed is compiled for a very specific setup. If, for example, you are using a different Python major version or a different PyTorch version, the FlashAttention binary might not load or might crash when imported. Then we check whether CUDA is available using torch.cuda.isAvailable. If this prints false, it means PyTorch cannot access an NVIDIA GPU and FlashAttention will not run. In that case, the notebook would typically fall back to baseline CPU or standard PyTorch attention experiments depending on how it's written. If CUDA is available, we print out several GPU details. We print the GPU name to confirm which device we're using, then we print the CUDA runtime version that PyTorch is built against. After that, we print the compute capability, which is a key number for FlashAttention. FlashAttention requires newer NVIDIA architectures, and compute capability is how we verify that. We also print whether BF16 is supported, because BF16 is a common data type used in modern deep learning for speed and memory efficiency, especially on newer GPUs. Now let's interpret your output. You are running Python 3.12.12 on Linux and PyTorch 2.8.0 with CUDA 12.8, which is exactly aligned with the installation we did earlier. CUDA is available and the GPU is an NVIDIA L4. The compute capability is listed as 8.9, which means this GPU is from the Ada generation and is definitely newer than Ampere. That's a good sign because it is in the supported range for FlashAttention style kernels. Finally, BF16 support is true, meaning your GPU and PyT ORCH build can use BF16 acceleration, which is very useful for performance benchmarks. The goal of this section is not only to confirm that FlashAttention can run, but also to set expectations about performance. Even if FlashAttention is not installed, PyTorch's own scaled product attention can sometimes choose an optimized kernel internally, like flash or memory-efficient attention, depending on your system and build. In the next steps, we'll check which attention backend is being used and then move into correctness and benchmarking. In this block, we're trying to answer a very practical question. When you call PyTorch's scaled.product attention, what implementation does PyTorch actually use under the hood? PyTorch can compute attention in multiple ways. Some ways are plain math and easy to understand but slower, and some ways use highly optimized GPU kernels that are much faster and use less memory. Which one you get depends on your GPU, your PyTorch build, your CUDA version, and sometimes even tensor shapes and data types. The first part of the code checks whether a special context manager called SDP_kernel is available. Think of SDP_kernel as a control panel that lets you enable or disable different attention kernels for experimentation. Not every PyTorch version exposes it, so the code uses a try and accept block. If the import succeeds, we print that SDPA kernel flags are available. If not, we print a message explaining that this feature is missing in that version. Your output shows it is available, which is great because it means you can explicitly control which attention backend PyTorch is allowed to use. Next, the code inspects an enum called SDP backend. This enum lists the possible attention backends PyTorch knows about. The reason this introspection is a bit complicated is that enums can be exposed to Python in different ways depending on how PyTorch was built. So the code checks multiple possibilities, the clean Python enum interface, and if that's not present, it falls back to scanning for common backend names. This is simply defensive coding to make sure the notebook works across more environments. In our output, the enum members are clearly listed: math, FlashAttention, efficient attention, and Cadden attention, plus a few extra internal values. Here is what these mean in simple terms. Math is the straightforward implementation that does attention using standard operations. It's reliable and works everywhere, but it's usually slower and can use a lot of memory. FlashAttention is the fast kernel-style implementation that reduces memory traffic and improves speed, especially for larger sequences. Efficient attention refers to another optimized path that is often memory efficient and can outperform the math backend. And QDNN attention means PyTorch may delegate attention to NVIDIA's QDNN library when that path is available and beneficial. Finally, the code prints the current on or off switches for each backend. These flags do not mean PyTorch will always use every backend. Instead, they mean the backend is allowed to be used if conditions are right. PyTorch still chooses among them at runtime based on things like tensor shapes, D-type, dropout settings, causal masking, and what your GPU supports. Our output shows that all 4 backends are enabled: Flash, memory efficient, math, and QDNN. That's an ideal setup for benchmarking because it means PyTorch has access to the full set of optimized options. The key takeaway is that enabled does not equal chosen. In the next steps, we'll typically run a small test attention call and confirm which backend is actually selected for our specific inputs because the final decision is made dynamically. In this section, we're going to check whether FlashAttention is actually installed correctly and usable in this environment. Even if the installation command succeeded, it's still possible for an import to fail at runtime due to missing CUDA libraries, GPU incompatibility, or version mismatches. So this block is a reality check before we start using FlashAttention in correctness tests and benchmarks. The code uses Python's importlib module, which lets us import a module dynamically by name. We could do a normal import FlashAttention, but using importlib makes it easier to catch errors and print a helpful message instead of crashing the notebook. We set up 3 variables: flash OK to track whether the import worked, flash reason to store the error message if it fails, and flash to hold the imported module object if it succeeds. Inside the try block, we attempt to import flash_atten.flash_atten_interface. This module contains the practical functions we want to call for fast attention on the GPU. If the import works, we set flash OK to true. If anything goes wrong, we catch the exception and save the reason as a readable string. This makes debugging much easier because you immediately see why FlashAttention is not available. After the import attempt, we print whether FlashAttention is available. If it's not available, we print the reason. This could be something like CUDA not found, wrong GPU architecture, or binary incompatible with this Torch version. If it is available, we print the module object and then check for 2 important functions: FlashAttenFunc and FlashAttenKVPactFunc. These 2 functions represent common ways to call FlashAttention. The first one, FlashAttenFunc, expects you to provide query, key and value tensors separately, often called Q, K, and V. That's the most direct way to think about attention. You compute attention weights from Q and K and then apply those weights to V. The second one, FlashAttenKVPactFunc, expects Q, K, and V packed together into a single tensor. Packing is often used for performance because it reduces overhead and can improve memory access patterns, especially when you generate Q, K, and V in a single fused projection layer. Now, looking at our output, everything is perfect. FlashAttention is available, the module imported successfully, and both FlashAttenFunc and FlashAttenKVPactFunc exist. That means our environment is correctly set up to run real FlashAttention kernels on the GPU, not just fall back to PyTorch baselines. In the next part of the tutorial, we'll start using these functions and compare them against a reference attention implementation to confirm correctness before measuring speed and memory. In this section, we're building a small controlled test case so we can compare 3 different ways of computing attention. The goal here is to understand attention conceptually and then verify that faster implementations still produce the same results as the textbook version. We will compare a naive implementation, PyTorch's built-in scale dot product attention, and FlashAttention, if it is installed and available. We also test both non-causal and causal attention, because causal masking is essential for autoregressive language models like GPT, where each token is only allowed to look at the past. The first thing you see is a short comment explaining that these implementations are meant for education and benchmarking. This is important because the naive implementation is not the one you would use in production. It is simple and clear, but it is also inefficient for large sequences because it explicitly constructs a full attention matrix of size, sequence length by sequence length. That matrix can become huge and quickly dominate memory usage, which is exactly one of the problems FlashAttention tries to solve. Now let's look at the function attention naive. This function implements the classic attention formula, softmax of q times k transpose, scaled by the square root of the head dimension, then multiplied by v. The inputs q, k, and v each have shape b, h, s, d. Here, b is batch size, h is the number of attention heads, s is sequence length, and d is the dimension per head. The output has the same shape because attention produces a transformed version of the values for every position and every head. Inside the function, we compute a scale factor equal to d to the power of -1/2, which is the same as dividing by the square root of d. This scaling is not optional. Without it, the dot products grow too large as the dimension increases, which makes the softmax become extremely peaky and unstable. Then we compute the raw attention scores using a matrix multiplication between Q and the transpose of K. This produces a tensor of shape, B, H, S, S, meaning for every batch and head, we have an attention score between every query position and every key position. If causal mode is enabled, we apply a causal mask. The mask is an upper triangular Boolean matrix that marks future positions as invalid. For example, position 5 is not allowed to attend to positions 6, 7, and beyond. We create this mask with torch.true and then use mask.fill to replace all disallowed scores with negative infinity. The key idea is that when we apply softmax, values of negative infinity turn into zero probability, meaning the model cannot attend to those future tokens. After masking, we apply softmax across the last dimension, which converts raw scores into attention probabilities that sum to 1. Finally, we multiply these attention probabilities by v, which produces the weighted combination of value vectors. This gives us the final attention output with shape B, H, S, D. The second function, attention SDPA, is a wrapper around PyTorch's scaled dot-to-product attention. It computes the same mathematical operation as the naive version, but it lets PyTorch decide the best way to execute it. Depending on your GPU and your PyTorch build, this call may use a fast kernel internally, such as FlashAttention or another memory-efficient implementation, instead of explicitly building the full SS attention matrix. The isCausal flag tells PyTorch whether to apply causal masking, just like we did manually in the naive implementation. The big picture is this. Both functions represent the same attention mechanism, but they differ massively in performance and memory behavior. The naive version is the clearest way to learn the algorithm, while PyTorch SDPA is the practical and optimized version you would normally use. In the next part of the notebook, we will create actual random Q, K, and V tensors and run these functions side by side to confirm that their outputs match, and then we will add FlashAttention into the comparison. In this block, we are setting up the actual tensors that we will feed into the attention functions. This is where the theory starts to turn into something concrete that we can run and compare. The goal is to create a small but realistic attention workload that works both on GPU systems with FlashAttention and on CPU-only systems for learning and debugging. We begin by selecting the device. If CUDA is available, we use the GPU by setting the device to CUDA. Otherwise, we fall back to CPU. This makes the notebook portable, so it can run on different machines without modification. Next, we choose the data type. On GPUs, FlashAttention is typically used with half-precision formats, like float16 or bfloat16, because these formats are much faster and more memory efficient than full 32-bit floats. In this example, we use float16 when running on CUDA. If we are on the CPU, we fall back to float32, because most CPUs do not efficiently support half-precision operations. This conditional choice keeps the code correct and stable across environments. Then we define the dimensions of our test case. B is the batch size, H is the number of attention heads, S is the sequence length, and D is the dimension of each head. The chosen values are intentionally modest. A sequence length of 512 is large enough to show meaningful attention behavior, but small enough that CPU users can still run the naive attention implementation without running out of memory or waiting too long. We also set a manual random seed using torch.manual seed, open parenthesis, 0 close parenthesis. This is important for reproducibility. By fixing the seed, we ensure that every run of the notebook generates the same random tensors. This makes output comparisons fair and makes debugging much easier, especially when checking whether different attention implementations produce the same results. After that, we create the query, key, and value tensors using torch.random. All three tensors have the same shape, B, H, S, D. We place them on the selected device and use the chosen data type. The key and value tensors are created using torch.random-like, which guarantees they match the shape, device, and D type of the query tensor exactly. Finally, we print out the shapes, data type, and device of the query tensor. This is another small sanity check that confirms everything is set up as expected before we move on to running attention. In the next step, we'll start computing attention outputs and directly compare the naive implementation, PyTorch SDPA, and FlashAttention for correctness. In this section, we perform correctness checks. The key idea is simple. FlashAttention is an optimization, but it must still compute the same mathematical result as standard attention, up to small numerical differences. Because we are using half precision like FP16 or BF16, tiny differences are normal. Different kernels may accumulate floating point rounding error in slightly different ways, so we do not expect bit-for-bit identical outputs. Instead, we compare results using a tolerance-friendly metric. The code starts by trying to determine whether FlashAttention is actually usable on this machine. It defines a helper function called isAmpere or newer. FlashAttention requires modern NVIDIA GPUs, specifically Ampere generation or newer, which corresponds to compute capability SM80 or higher. The function checks the GPU compute capability and returns true if the major version is at least 8. If CUDA is available, the script prints the GPU name and its compute capability so we can confirm what we are running on. Next, we make a decision. If the GPU is older than Ampere, we set FlashOK to false and store a clear explanation. Otherwise, we try to import the FlashAttention interface module and check that the core function FlashAttenFunc exists. This is an important detail. Sometimes a module can import, but the function you need might not be present due to an incomplete install or a mismatched build. At the end of this section, we print whether FlashAttention is usable, and if not, we print the reason. Now we define a small utility function called max.abs_err. This computes the maximum absolute error between two tensors. In other words, it looks at every element in the output and finds the single largest difference. This is a strict metric because it focuses on the worst-case mismatch. We also convert outputs to float 32 before comparing. This is important because comparing directly in float 16 can hide differences due to limited precision. Converting to float 32 makes the comparison more reliable and easier to interpret. The heart of this section is the function check1, which runs the comparison for either non-causal or causal attention. First, it computes the attention output using the naive reference implementation. Then it computes attention using PyTorch's scale dot product attention. We compute the maximum absolute error between naive and SDPA and print it. This tells us whether PyTorch's optimized attention is behaving correctly relative to the reference. If FlashAttention is usable and we are on CUDA, we also compute the FlashAttention output. But before calling FlashAttention, we must fix the tensor layout. Our tensors are currently shaped as BHSD, meaning batch, heads, sequence, head dimension. However, FlashAttention's FlashAtten func commonly expects BSHD, meaning the sequence dimension comes before the heads. So we transpose dimensions 1 and 2 to convert from BHSD to BSHD, and then we call dot contiguous to ensure the data is stored in a contiguous memory layout. That contiguous step matters because many CUDA kernels assume contiguous memory for speed and correctness. After computing the FlashAttention output, we transpose it back to the original format, BHSD, again making it contiguous. Then we compute the maximum absolute error between the naive output and the FlashAttention output, and print that as well. Finally, the code calls check1 twice, once for non-causal attention and once for causal attention. Now, let's interpret our output. Our GPU is an NVIDIA L4 with compute capability 8.9, which is newer than Ampere, so FlashAttention is usable. The reported maximum absolute errors are around 1 to 2 thousandths. Specifically for non-causal attention, the maximum error is about 0.00098. And for causal attention, it is about 0.00195. These values are completely normal for FP16 computations, and the most important point is that PyTorch SDPA and FlashAttention match the naive reference to the same order of magnitude. That means our setup is correct and we can trust FlashAttention outputs for benchmarking. The takeaway of this section is that FlashAttention is not changing the attention algorithm. It is computing the same thing, but doing it in a way that is dramatically more efficient on the GPU. Now that correctness looks good, the next step is to measure performance, where FlashAttention typically shows large speedups and much lower memory usage, especially as sequence length grows. In this section, we move from correctness to performance. Now that we know all implementations produce essentially the same attention output, the natural question becomes, which one is faster in practice? Here we benchmark the wall clock runtime, meaning we measure how long each method takes to run, averaged across many iterations. We compare 3 options: the naive reference implementation, PyTorch's scaled dot product attention, and FlashAttention if it is available. The code begins by importing torch.utils.benchmark and Python's time module. Even though torch.utils.benchmark is imported, this particular snippet uses time.perfCounter directly to measure elapsed time. PerfCounter is a good timer for benchmarking because it has high resolution and is designed for measuring short durations. The function benchmark_fn does the timing work. First, it runs a warm-up loop. Warm-up is crucial on GPU workloads because the first few runs often include one-time overheads like kernel compilation, caching, memory allocation, or CUDA context initialization. If we time those first runs, our benchmark would be misleading. After warming up, the code synchronizes the GPU if we are on CUDA. This is one of the most important concepts in GPU benchmarking. GPU operations are asynchronous by default. That means Python might think an operation is done when it has only been queued, not fully executed. Calling torch.cuda.synchronize forces Python to wait until the GPU finishes all queued work, so our timer measures the real runtime. Then we record a start time, run the function many times, synchronize again if needed, record the end time, and compute the average time per iteration. Finally, we return the result in milliseconds, which is an easy unit to read when operations are very fast. Next, the function bench suite defines the benchmark set for either causal or non-causal attention. It creates small wrapper functions, fnaive and fsdp, that call the naive attention, and PyTorch SDPA implementations with the chosen causal setting. The naive implementation is expensive compared to the others, so the code uses fewer iterations for it by setting iters equals max of 5, iters divided by 10. This prevents the benchmark from taking too long while still giving a reasonable estimate. PyTorch SDPA is fast, so it uses the full iteration count. If FlashAttention is available and we are on the GPU, the code also benchmarks FlashAttention. Just like in the correctness section, we transpose the tensors into the shape FlashAttention expects, from B, H, S, D to B, S, H, D, and we make them contiguous in memory. Then we define fflash, which calls FlashAttenfunc with the same causal setting. This allows a fair comparison. All methods are computing the same logical operation under similar conditions. Finally, the code runs the benchmark suite twice, once for non-causal and once for causal attention, printing out a neat summary of timing results for each method. Now let's interpret our benchmark output. For non-causal attention, the naive method takes about 0.119 milliseconds. PyTorch SDPA takes about 0.026 milliseconds, and FlashAttention takes about 0.098 milliseconds. For causal attention, the naive method is slower, around 0.195 milliseconds. PyTorch SDPA is still very fast at about 0.025 milliseconds, and FlashAttention is about 0.097 milliseconds. The most important observation is that PyTorch SDPA is the fastest in both cases on our setup. This result can surprise beginners because they expect FlashAttention to always win. But it's normal for performance to depend heavily on input sizes, GPU architecture, and which SDPA backend PyTorch chooses internally. In our environment, PyTorch SDPA is likely dispatching to a highly optimized backend, possibly FlashAttention itself, QDNN attention, or another fused kernel, meaning SDPA might already be using a Flash-like fast path. Another key point is that our test size is relatively modest, with sequence length 512 and head dimension 64. For smaller sizes, overhead and kernel launch costs can dominate, and the best kernel can change. A subtle detail here is that FlashAttention appears slower than SDPA, but that does not mean FlashAttention is bad. It means that in this particular configuration, PyTorch's SDPA path is extremely optimized and is winning for these shapes and settings. In the next steps, a common follow-up is to scale sequence length upward, like 1024, 2048, or 4096, and then rerun benchmarks. That's where FlashAttention often shows dramatic advantages, especially in memory usage and in regimes where naive attention becomes impractical. The takeaway of this section is that benchmarking must be done carefully, and results must be interpreted in context. FlashAttention is a powerful optimization, but the actual speed winner depends on the kernel selection and the workload. Next, we typically benchmark memory usage as well, because even when speed differences are small, FlashAttention's biggest win is often reducing memory traffic, and avoiding the huge attention matrix that naive attention builds. In this section, we benchmark memory usage on the GPU. This is where FlashAttention often shines, because the classic attention algorithm creates an attention matrix of size S by S for every head and every batch. That memory grows with the square of the sequence length, which is why attention becomes so expensive when you increase context length. FlashAttention is designed to avoid materializing that full matrix, reducing memory pressure and enabling longer sequences or bigger batch sizes. The function peak membytes measures peak GPU memory allocated during a single forward pass of a function. This only works on CUDA, so the function immediately returns none if we are not using a GPU. If we are on CUDA, it resets PyTorch's peak memory tracker, clears cached memory, runs the function once, synchronizes the GPU to make sure the work is finished, and then returns the maximum amount of memory that PyTorch reports as allocated during that run. The reset and synchronize steps are important because GPU memory allocation is dynamic and asynchronous, so without these steps, the reported values can be inaccurate. Next, the function mem suite defines the memory benchmark suite for either causal or non-causal attention. It creates wrapper functions for naive attention and PyTorch SDPA, then measures the peak memory for each one using peak mem bytes. If FlashAttention is usable, it also measures FlashAttention memory. Just like before, we transpose the tensors into the shape FlashAttention expects, B, S, H, D, and make them contiguous so the kernel can run efficiently. After defining the suite, the code checks whether we are on CUDA. If not, it skips the memory benchmark. If we are on CUDA, it runs the suite for both non-causal and causal settings. Finally, it prints the peak allocated memory in megabytes, which is an easy unit to interpret. Now let's interpret our results. For non-causal attention, the naive implementation peaks at about 28.12 megabytes. PyTorch SDPA peaks at about 12.16 megabytes, and FlashAttention peaks at about 15.16 megabytes. For causal attention, the pattern is essentially the same. Naive is about 28.38 megabytes. SDPA is again about 12.16 megabytes, and FlashAttention is about 15.16 megabytes. The big takeaway is that the naive implementation uses far more memory than the optimized paths because it explicitly builds the full attention score matrix. You might notice that SDPA is using even less memory than FlashAttention in this particular run. That can happen, and it is not a contradiction. PyTorch SDPA is not a single implementation. It is a dispatcher. Depending on the GPU, D-type, and shapes, it can pick a memory-efficient kernel or a fused backend that is extremely optimized. In our environment, SDPA is very likely selecting an especially memory-efficient backend, which is why it beats FlashAttention on this exact configuration. The most important learning point is not which one wins by a few MIB at sequence length 512. The key point is the scaling behavior. The naive method's memory grows roughly with S squared, so increasing sequence length quickly becomes impossible. Optimized attention kernels aim to avoid storing the full S by S matrix, so their memory growth is much closer to linear in S. In the next step of a tutorial, a great demonstration is to increase S, for example, to 2048 or 4096, and show that naive attention's memory explodes while SDPA and FlashAttention remain manageable. In this section, we study how attention runtime scales as the sequence length increases. This experiment is extremely important because the main motivation behind FlashAttention is not just speed at small sizes, but scalability when context length grows. This is where naive attention becomes impractical and optimized kernels really matter. We start by defining a list of sequence lengths to test. If we are running on a GPU, we use lengths of 256, 512, 1024, and 2048. These values are large enough to clearly show scaling behavior without exhausting GPU memory. If we are on CPU, we keep the lengths much smaller because naive attention becomes very slow and memory hungry even at moderate sequence sizes. Next, we define a helper function called makeQKV. This function generates fresh query, key, and value tensors for a given sequence length. The batch size, number of heads, and head dimensions stay fixed. This is important because we want to isolate the effect of sequence length alone and not mix it with other variables. The function time attention measures how long a single forward pass of attention takes for a given method. Just like before, we include a warm-up phase to avoid one-time overheads, and we synchronize the GPU before and after timing, so the measurements reflect real execution time. We support 3 methods here: naive attention, PyTorch SDPA, and FlashAttention. For FlashAttention, we again transpose tensors into the BSHD format expected by the kernel. We then loop over sequence lengths and methods, recording the average runtime in milliseconds for each configuration. These values are stored so we can plot them afterward. This produces both printed numbers in the console and a visual plot, which makes the scaling behavior much easier to understand. Now let's interpret the printed results and the plot you see on the screen. The blue curve corresponds to naive attention. At small sequence lengths like 256 or 512, naive attention looks manageable. But once we move to 1024, runtime jumps sharply, and at 2048 it explodes to several milliseconds. This is the signature of quadratic scaling. Naive attention explicitly computes an S by S attention matrix, so doubling the sequence length roughly quadruples the work. The orange curve represents PyTorch's scaled dot product attention. Notice how flat this line is compared to the naive one. Even as the sequence length grows to 2048, runtime increases only slightly. This tells us that PyTorch is using a highly optimized backend that avoids materializing the full attention matrix and keeps memory traffic under control. The green curve shows FlashAttention. Its behavior is similar to SDPA. Runtime grows slowly as sequence length increases rather than exploding. In this particular setup, FlashAttention is slightly slower than SDPA at smaller sizes and slightly slower at the largest size as well. This is not a failure of FlashAttention. It simply means that PyTorch SDPA is already dispatching to an extremely optimized kernel on this GPU for these shapes. The most important takeaway from this plot is not which line is lowest by a few microseconds. The key takeaway is the shape of the curves. Naive attention scales quadratically and quickly becomes unusable. SDPA and FlashAttention scale much more gently, closer to linear behavior, which is exactly what we want for long context models. This scaling experiment explains why FlashAttention matters in real systems. When you move from sequence length 512 to 4096 or beyond, naive attention is no longer an option at all. Optimized attention kernels are what make modern large language models, long context transformers, and multimodal models feasible on real hardware.